The maximum shear stress theory is normally used in the case of ductile material, and we know the ductile material will fail by yielding. This theory is created by Coulomb, Tresca or Guest, is also called as the Coulomb theory or the Guest theory, or is also called as Tresca theory. And this theory says that any mechanical component subject to any combination of loads will fail whenever the maximum shear stress. So maximum shear stress means absolute. So you have to convert the two-dimensional problem into three-dimensional problem, and one of the stress you have to consider equal to 0 when we convert from two-dimensional to the three-dimensional, and then you have to compare that value of the tau absolute maximum with the shear strength of the material, that is a SSY, which is obtained by the standard tension test. So according to the maximum shear stress theory, whatever the value you obtain as tau absolute, the maximum shear must be less than value of SSY, that is a yield stress in shear. And according to the tension test, already we have proved the value of SSY is equal to SYT by 2. Now how to calculate the value of tau absolute maximum, that concept also we have done by considering the plane state of a stress and finding the value of two principal stress sigma A and sigma B, and one principal stress will assign equal to 0, and they will arrange in the order of sigma 1 greater than equal to sigma 2 greater than equal to sigma 3. So we'll consider here a plane state of a stress acting along the x direction is equal to sigma x, shear stress equal to tau xy, and the normal stress acting along the y direction equal to sigma y. Using the sigma x and tau xy and sigma y, we can calculate two principal stress sigma A and sigma B. Using the standard relation that we are familiar is sigma x plus sigma y divided by 2 plus minus under root of sigma x minus sigma y divided by 2 whole square plus tau xy square. So we are very much familiar with this procedure now. And the third value of a principal stress will take equal to 0. And then you have to arrange the three principal stress in such a order that we have sigma 1 will be greater than equal to sigma 2 will be greater than equal to sigma 3. Sigma 1 can be equal to sigma A or sigma B. It entirely depends upon the value of sigma and sigma B. So you have to first arrange the three principal stresses in the form of sigma 1 greater than equal to sigma 2 greater than equal to sigma 3. Now here the maximum Mohod circle will form using sigma 1 and sigma 3, and the maximum Mohod circle radius will be same as equal to tau max. So and that value of tau max will called as tau max absolute value using the 3 Mohod circle method, and is given as the value of sigma 1 minus sigma 3 divided by 2. If you remember the video that is on Mohod circle, how to find out the value of tau max absolute. So we'll consider here case 1. For this case, we'll assume here that the value of principal stress sigma A is greater than equal to the principal stress B and is greater than equal to 0. In this case, the maximum value is sigma A, so we'll assign the value of sigma 1 is equal to sigma A, sigma 2 is equal to sigma B, and the least value is assigned equal to 0. So third principal stress you assign equal to 0. If this situation will occur, then according to the definition of maximum value of the shear stress, that is the overall maximum shear, will be equal to tau max absolute is equal to sigma 1 minus sigma 3 is same as equal to sigma A divided by 2. And if the value of sigma A is a positive value greater than equal to 0, but the value of the principal stress sigma B is negative value, that is less than 0. So the highest value here is sigma A. So we'll assign the value of sigma 1 equal to sigma A. Lowest value is equal to sigma B, that will assign as sigma 3. So in this case, we'll make the value of sigma 2 is equal to 0. And the least value is sigma 3 will be equal to sigma B. In this case, we'll get the value of tau max absolute value. So we have tau max absolute in this case. By definition, sigma 1 is same as sigma A and sigma 3 is equal to sigma B. So in this case, we will get sigma A minus sigma B divided by 2. Now consider the case 3. If we have the value of 0 is greater than equal to the value of principal stress sigma A is greater than equal to sigma B. So both the stress sigma A and sigma B are negative value, and the maximum value of the stress here is 0, so that will assign equal to sigma 1, which one is the highest value. So sigma 1 will be equal to 0, and the least value will assign to sigma 3. So in this case we have sigma 3 will be equal to sigma B. So absolute maximum shear tau max absolute by definition is again remains same, equal to sigma 1 minus sigma 3 by 2. Sigma 1 is 0 and sigma 3 is equal to sigma B. So we'll get this value is equal to sigma B divided by 2, but negative value. So our value of tau max is fixed here, that is the tau max absolute value will be either sigma A by 2 or sigma A minus sigma B by 2 or minus sigma B by 2 if we arrange the three principal stresses in the order of sigma 1 greater than equal to sigma 2 greater than equal to sigma 3. To find out the shear strength of the material, we have to carry out the simple tension test. In the simple tension test, the state of a stress consists of purely tension, and for yielding condition, this value of sigma x will be same as equal to SYT. So only one stress will involve this time, that equal to sigma x. So in this case we have sigma 1 will be same as equal to sigma x is equal to SYT. Other two stresses we have to make equal to 0, that is sigma 2 equal to 0 and sigma 3 equal to 0. This value will give you the torsional shear strength, that is SSY. And according to the definition again, this value will be sigma 1 minus sigma 3 by 2. We have sigma 1 equal to SYT. Sigma 3 will be equal to 0, so we have SYT divided by 2. So we require this information here to develop the stress envelope in the case of maximum shear stress theory. In the first case we have sigma A is greater than sigma B greater than 0, then the maximum value will be equal to sigma A, so we assign the sigma 1 equal to sigma A, least value equal to 0, so sigma 3 equal to 0. By definition of a overall maximum shear, we get sigma 1 minus sigma 3 by 2. Sigma 1 is same as sigma A, sigma 3 equal to 0, so we have absolute maximum shear will be sigma A by 2. If we consider here the sigma A is a positive value and sigma B is a negative value, in that case the maximum value sigma 1 will be sigma A and sigma 3 will be sigma B, and the absolute maximum shear will be sigma A minus sigma B by 2. And if both the value are less than 0, that is a negative value, then the highest value in this case is 0, so we assign sigma 1 equal to 0, and the least value will assign equal to sigma 3, so we get tau max absolute value is equal to minus sigma B by 2. And we know that in the simple tension test the only stress produced is sigma x, and since we want here yielding will take place at SYT, so we have sigma 1 equal to SYT and other two stresses will make equal to 0, so we have torsional shear strength will be equal to SSY is equal to SYT by 2. So according to the maximum shear stress theory, which says that for any mechanical component subjected to any combination of load will fail whenever the maximum shear stress, that is the value of the absolute value of the shear, that is tau max absolute, must be equal to torsional shear strength, that is SSY divided by factor of safety. SSY is always greater than tau max absolute, so factor of safety will be greater than 1. But we have torsional shear strength is same as SYT, so SYT divided by 2 times of factor of safety. Whether we have case 1, case 2, case 3, our tau max absolute is given as sigma 1 minus sigma 3 divided by 2 is equal to SYT divided by 2 factor of safety. 2 and 2 will cancel here, and always it is true that we have sigma 1 minus sigma 3 is equal to SYT divided by factor of safety. So using this information we can develop the stress envelope in the case of maximum shear stress theory. So for maximum shear stress theory, we have taken the three cases. Case 1 is tau max absolute is equal to sigma A by 2. Then in the case 2, we have tau max absolute is equal to sigma A minus sigma B by 2. And case 3, we have tau max absolute is equal to minus sigma B by 2. Now whenever we consider the tau max value, there are the two values for the tau max. Suppose I draw here the Mohod circle using the sigma axis and the tau axis. This one is same as equal to sigma 3. Then we have sigma 2 and then we have sigma 1. So one more circle you can draw between sigma 3 and sigma 2. So that more circle will be somewhat like this. Then second more circle you can draw between sigma 1 and sigma 2. And the maximum value correspond to sigma 1, sigma 3 always. So in this case, one value will get positive value of tau max. And the second value is negative value of tau max. As far as the case 1 is considered and the case 3 is considered, we have tau max absolute is sigma A by 2 and tau max absolute is equal to minus sigma B by 2. So for case 1 and case 3, this value of tau max absolute will take as a plus minus. So we have plus minus tau max absolute value is either is equal to sigma A by 2 or is equal to minus of sigma B by 2. And we know the value of tau max absolute value is same as equal to SYT divided by 2. So 2 and 2 will get cancelled here and we have one value of sigma A will be equal to plus minus SYT and second value we have sigma B is equal to plus minus SYT. So we can form the envelope here using the three cases. For that one, we have first equation is sigma A is equal to plus minus SYT and sigma B is equal to plus minus SYT. And for ductile material, the value of SYT is same as equal to SYC. That is the yield stress in tension is same as the yield stress in compression. So in this case, we have taken the factor of safety n is equal to 1. So we can draw the friends here. Let here x-axis represent sigma A, y-axis represent sigma B, we have negative of sigma A and we have negative of sigma B. For case 1, sigma A and sigma B both are greater than 0. So this one is a zone where we have sigma A and sigma B are greater than 0. And for case 3, both are negative value. That is in the third quadrant, we have both are negative value. So this one is representing the case 3. So this one is case 1 where we have both the principal stresses are positive and this one is representing the case 3 where both the principal stresses are negative. First equation will get that is sigma A is plus minus SYT. So you have to draw here one vertical line such that the value of sigma A remain constant. And second line you have to draw for sigma B, that is positive SYT. So this value is same as equal to SYT and this value is also equal to SYT. So for case 1, if your part is inside, it is a safe design. Whereas one value of sigma A is minus SYT and the second value of sigma B is equal to minus SYT. Now for this region you have to show the value of minus SYT. So I have to mark here minus SYT, that is same as equal to SYC, and somewhere I have to mark here SYC. So if I draw the vertical line through SYC, it represents here the value of sigma equal to minus SYT, and the horizontal value represent here sigma B is equal to minus SYT, which is same as equal to SYC. So these two zones will satisfy the case 1 and case 3. Inside the part is safe and outside the part is fail. And according to the case number 2, we have tau max is equal to sigma A minus sigma B by 2. So that equation I will write here as tau max. Again we are trying for boundary condition. So we have tau max equal to sigma A minus sigma B divided by 2. And this value is again equal to limiting value for the fence will be plus minus SYT divided by 2. That is the value of sigma A minus sigma B is equal to plus minus SYT. Now sigma A is greater than 0 and sigma B is a negative value. So sigma A is positive value and sigma B is negative value. That is for this zone we are discussing the envelope. And let's check what you get from this one. Sigma A is nothing but our x-axis. Sigma B is nothing but our y-axis. So we have plus minus SYT. Y will shift on the right hand side, we'll get y. Then we have x will be minus plus SYT. Now this one is a standard form of equation which is given as y is equal to mx, where m represents slope and c represents here the y-intercept. In this case we have coefficient of x is 1, so we have slope is equal to 1, means theta is equal to 45, and we have y-intercept that is equal to c is equal to plus minus SYT. So for this zone you have to construct one straight line which is the slope is equal to 1. That is, you have to join the SYC is equal to SYT, because SYT and SYC they are identical value. So if you join them, then you will get a slope is equal to 1. And here the y-intercept is equal to minus SYT, that is same as equal to SYC. So join SYC and SYT, that will represent our case 2. And second time we have the y-intercept is positive, that is this intercept is positive. So if I join the SYC with SYT, I will again get a slope equal to 1 and the y-intercept is equal to SYT. So this one is become the envelope, that is a graphical representation of a maximum shear stress theory, or it is also called as a stress envelope for maximum shear stress theory. So inside region anywhere will be the safe region and outside it will be fail. So failure will occur outside because the value will exceed than SYT or SYC, then it is a failure. Maximum shear stress theory you have to use for predicting the failure of a ductile material, but this theory is little bit conservative. So instead of maximum shear stress theory, distortionary theory is normally used in the case of ductile material. We'll discuss this part later on. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.